So let's start. Welcome everybody to this course at Aalto University, Parametric Engineering. I'm super excited and happy that we could invite Jerry Danza for this workshop. Actually, he was invited already 1 year ago, but at that time he was supposed to come to Aalto University in person, and then as you know, we were all surprised by COVID, and so the whole thing got cancelled. So then after a couple of weeks, Jerry reconfirmed that he will join again in 2021. So here he is again, and I'm very happy that he agreed and will do this workshop on the following Thursdays. So it's always 2 hours more or less of workshop. And for the students who want to participate, it's 3 credit points for the workshop, and then you can gain another 3 credit points for a small project after that. But you can read everything on my courses if you are signed into that, so you will find all the information there and maybe also later some updates. Also, thank you for the guys from Rumble who joined in. It was a bit difficult, as I learned, for you to arrange your working schedules because it was a bit on short notice, and but ESCO is always in good contact with me, so I was very happy to invite you to this workshop, and hopefully you can also get something out of this, I'm quite sure. Jerry Danza, I would like to introduce him very briefly. I know him for probably 12-13 years already. We first met in 2008 or 9. Also in the framework of tensile structures, when I was involved in a master course in membrane and membrane structures mainly, and where he was teaching softwares and how to deal with these things in a digital environment. And this brings it exactly to the point, because Jerry is, from his background, first of all, an architect located in Italy, in Naples. And for many years now, he developed a software. Initially, it was the Forten software, and then it changed its name, and the package of the software increased dramatically for this IXCube. Nowadays, he also was focusing on different algorithms and methods in how to generate and how to do the form finding in the background. Maybe he will also explain a bit about that later. But basically, maybe some of you know Rhino Membrane, which he also was involved from the digital and the coding side, together with Lienhardt and Professor Pletzinger at TU Munich. And nowadays, it's kind of fully implemented in the Rhino Grasshopper environment. So it also can use and utilize this parametric approach for tensile structures. So he's a real expert in architecture, of course, but also in all the technical questions from form finding to patterning to materials and so on, of course, with his software. And he has his company selling also this software for professional use. And what we are using today is basically the full package, which is a bit limited in how long you can use it, but this is basically the fully professional environment that you are introduced to. So thanks, Jerry, for joining this course. I really appreciate that you're always so super flexible, and I was a bit excited also for the time shifts and the time zones. So I was not sure if we will really meet at 9 or 10. So for us,
actually, you sent me the email because I was not.
Yes, I was already preparing a lecture of 1 hour just to bridge this gap. Okay. Thanks, Jerry. Again, the floor is yours, and I will mute myself. I think you can join later, or you can share your screen. Hopefully,
thank you. Thank you for the introduction. Yeah, let me test this screen sharing. So because I have a few screens. Oh, it's asking me. Okay, so I think this one.
Yes, it works.
Fine. So we can start. Thank you for your introduction. And yes, the first thing that I want to do, since I think we are going to have a lot of hours of lessons, and we will talk about a huge amount of things. I want to introduce you first on the techniques that we use to do form finding. I think everybody has at least a basic idea what the form finding is. The main problem is very simple. To make tensile structures or to use them as a structural element, we need to find a shape, basically a shape where the main two things that we need is the geometry and the pre-stress of the membrane. So a tensile structure does not exist if we do not have a pre-stress field. It's not only geometry. We are using it as architects to design something like something with concrete or with steel, where we design it and we know that it's going to work. With membranes, it's not like that. We need to go through this form finding process. So understanding how it works and how the methods that we're going to use, the techniques that they're based on, it's quite important to understand how to do what we want to do and not what the computer wants to give to us. So just a brief introduction to the history. Everybody knows the Munich Olympic Stadium, and this is one of the first jobs, first works that Fray Otto did in the 70s. At that time, there were no computer softwares to do this, and so you see here on the right, this is the physical model that they used, and the main goal was to calculate the pre-stress in the cables using the physical model. Clearly, it was quite difficult. They calculated that a mistake of 1 millimeter in the model was going to generate a mistake of 50% in the cable pretension. So you understand that it's not feasible to do a project using these models. Well, they started doing research at that time. Yeah, a few. This is another example of form finding. This is a bridge here near near my office down here, designed by Musmeci. And it's clear how he did a form finding to design this bridge. You see here, this is a physical form finding. And the nice thing is that once we have a shape that is in a poor pretension, a tension field, we can invert it and put it upside down, and it becomes in poor compression. And this is what he has done here to design this bridge. So as I have underlined it, a tensile structure is made out of form plus pretension. So you always have to take care of these two fields. Well, we're not going into the math, but just to understand how these techniques work is interesting when you start, and then we'll see them later in the software. The first and one of the most used methods, even from Fray Otto team, is the force density method. This is very nice because it's very, very simple technique. Basically, we make a model that is a mathematical model made out of nodes and springs, elements that connect the nodes. And we want to find a shape where all these spring elements have a pre-stress or in tension, have a positive tension. Clearly, the goal is to find the nodal coordinates. In a very simple way, we can write down a system of equilibrium equations. But the problem is, if you try to do it, you'll see that the forces are unknown and the coordinates are unknown. So basically, nothing is known. And writing down the system of equilibrium equations, we get that the length of the elements we have under the equations, the length of the elements, that is the square root of the coordinates. And clearly, it's a nonlinear problem. This technique that has been developed by Škec in the 70s makes it very simple. If we think about the problem, the length of the elements are positive. We don't have negative length. The forces that we want are positive because we want all the elements to be in tension. So the ratio of the force over the length is always a positive number. If this is a positive number, we can take off the force and we can take off the length, because these values here compare in the equations, and we put an unknown, call it a C value. That's the first density value. This very simple technique, once you assign a field of C values, you get a pre-stressed shape in a very, very fast way. So clearly, once we have defined the boundary conditions, the points that are connected, and the topology means the net, the connections between the nodes and these springs, we can generate a huge amount of shapes just changing the set of first density values. So this has been a very, very nice technique, and has been used in the past 30 years for generating a huge amount of tensile structures. Another technique that we will not show is the dynamic relaxation. This has been developed in England by the Bath University and people coming out from the Bath University. And basically it's based on equilibrium, dynamic equilibrium of the shape, where the energy is when the energy reaches a peak, they reset the velocities and everything, and the shape goes to equilibrated position. It's a very nice method, but we will not discuss about that. Then clearly we have many people have developed non-linear finite element analysis to find the shape of the tensile structure. But clearly it has a big problem or a drawback, that we have huge, very large displacements in these fields. When we start from an unknown shape and we want to find the final shape, the displacements are very large. So generally, finite elements are not so good for doing this, and they get quite unstable. The new entries is the update reference strategy, and this has been developed by the Munich University by Professor Bletzinger, and the natural first density method that has been developed by Rui Paoletti, University of São Paulo. And we will show the first density method, the nonlinear analysis method, the update reference strategy, and the natural first density method. So basically, we can choose any of these methods when we make a shape form finding. In a very simple way, if we look at all the membranes that have been built, we see that if we are using a PVC material or a woven material, we have two main directions of the stress, and we call them the warp and the weft stress, or the warp or the fill. And even on the surface, we have two main directions. You see them here with these red and blue arrows. Basically, what these are very important when we design a tensile structure, because this is here we have highlighted the main stress direction, the direction where the main stresses flow. So it's an information that we need to keep in mind of, because when we are going to build these tensile structures, we want to layer out in the direction of the main stresses the fibers of the membrane. So if we have the membrane made out of warp and weft, clearly we want to put on these two main directions the fibers warp and the fibers weft. So if we look at the IPAR, for example, and we do a patterning, our patterns will go from high point to high point, because we want that the fibers go or put or layered on the main stress direction. Clearly, this is not a problem if we are using ATFE cushions or ATFE material, since ATFE is a material with constant properties in all directions. We can use any kind of patterning that we want. The nice thing about tensile structures today, we see, if you're Rhino Rhino fans, from a few years, we see that there's a very large production of form finding methods that are not really related to tensile structure form finding. I call them finding the form more than form finding. Finding the form means that we put a number of rules and we find a number of shapes based on these rules. So we're finding a form based on a number of rules. It's not really what we do with tensile structures. In tensile structures, we are finding the minimal energy. Okay, the principle on the back of the tensile structure is that we want to find out the minimal surface or the minimal energy of forms, and we can find these forms in nature in so many different examples. This is a flower where the distribution of these leaves follows the minimal energy principle. The same we see in the net, the spider net. This is a minimal energy spider net. Here you see that this is a perfectly shaped tensile structure, cable net. The same clearly with bubble soaps. Bubble soaps are a special case of minimal energy. These are minimal surfaces. Minimal surfaces have a very nice property. The stress in the membrane is constant in all directions. So in each point of the bubble soap, we have a uniform stress for all directions. So the stress tensor, mathematically speaking, is very, very simple, and we have a perfect usage of the material because the stress is constant in all directions and equal in any point of the surface. And these are generated, mathematically generated minimal surfaces, computer generated minimal surfaces. On the right, this is a Costa surface generated with the update reference strategy. So clearly, it's up to you, it's up to the architect if he wants to use minimal surfaces or not. Basically, what happens in reality is that the minimal surface would be the best choice from an engineering point of view. But it happens quite often that when it comes to design a tensile structure, we have a lot of constraints. So we have to go a little bit away from the minimal surface and choose different stress levels. Another example, Fraiotto, a very famous example, where we have this eyelet, and we see, maybe if we have time, we can see how to model one of these using the FDM or the natural force density. Clearly, at that time, there was no membrane. I mean, the technical membranes that we have today were not available. So the initial works of Fraiotto were made of these cable nets covered by plastic material. Another example of the Fraiotto. These are very nice umbrellas by Bodarash. And the Bodarash tends to use always minimal surfaces. So these are not really conical shapes. These are tend to be minimal surfaces. Another thing to underline when you are thinking, if you're designing or you're and you want to really make a project with a tensile structure, don't think that the tensile structure, the membrane, is the main problem. The details, the connections, the foundations, any detail and any steel element is the overall tensile structure. So never forget about the supporting structure, the quality of design of the steel, of the connections, and clearly of the patterning. Here we see a very nice patterning here with this Arabic design. So everything is important in the same way. This is another the new trend in from 5-6 years. The ATFE cushions are getting really popular among lightweight structures. This is a project by FATL Design, New York, and clearly the ATFE cushions are, from a geometrical point of view, quite simple because they're just cushions. We have a limit that we cannot make them. The width of the cushions must be in the range of 2.5-3 meters. But then you can generate how long you want these cushions. Clearly, the stabilization is made out of the internal pressure. So geometrically speaking, they're quite simple because there's just a cushion with an internal pressure. But there are a huge amount of possibilities for generating lightweight architecture and very, very nice solutions. In this case, we see this lightning. These are Americans, so they love this. This is a casino, so this lightning is very nice, but makes a lot of difference. This is an ITFE question that we made some years ago at the MS Institute for an institute for government a government building. So we covered the main yard with this ATFE question. This was a nice thing. We followed, I think, more than 10 years ago. And this was a temporary pavilion for the MoMA New York. And clearly, this has nothing to do really with a conventional membrane, you can see. But we still follow the principles of a tensile structure. I mean, it's a tensile structure, but the membrane is made out of these small plastic pieces sewed together, welded together. But the overall final pavilion, it was a temporary pavilion, had a very, very nice effect. And another example that we did in Argentina. What to say here is about the strange conical shapes that the architect designed. And you see that it's not really a conical shape, it's a double conical shape. And this is a bus station. So clearly, once you know how to use how the main principles work, you are really able to do a huge amount of different things and new designs. Clearly, keep in mind again that the patterning is what really people see. So the quality of the space is underlined by the quality of the patterning that design these lines in space. So I always recommend to look at the patterning and make a high quality of these because they are really what you're going to design. So just a few words about what happened in the past years. We could go fast on this, but in the 70s, the main problem of designing tensile structures was done by big engineering firms, Geiger engineers, Burrow Apple, and those people there. And clearly, they developed their inside solutions for that. And so we saw that only big stadiums or big projects were affordable by doing tensile structures could be done only for huge projects. It was very expensive for making those projects, for running analysis and all that stuff there. In 2000, we saw a little bit that the software was more available. And so it was available to engineering firms, construction companies, and even to big architectural offices. And we started seeing commercial packages coming on the market. Today, luckily, we have a huge amount of available software. We can use Rhino, for example, with Grasshopper and with Kangaroo to design tensile structures. And so the main technology is available almost to anybody. And this is a nice thing to spread around the tensile structures in those things. Well, this is since we are going to talk about engineering. Clearly, we will focus in these lessons using Icecube connected with Rhino and Grasshopper. But clearly, the nice thing about this workflow is that you can connect your job to basically any software out there, so from Revit to Rhino to Grasshopper to Unity and so on. And I think this is the main change today, that we are able to use a huge amount of different technologies for the purpose of getting into our project, getting to the final project in the easiest, fastest way, and the high quality, of course. So this is Joe. I think you already know about these features we have inside Grasshopper for evaluation of the heating, the sun, the shading. Clearly, the shading is what we're interested in. This is a project made by entirely inside Grasshopper, and so on. So basically, we are able to run analysis in a huge run not only structural analysis. I mean, we can do a huge amount of different analysis algorithm project using Grasshopper as the main hub. We can do structural analysis, terminal analysis, fluid flow analysis, solar radiation, and so on. So it's a good thing that learning these techniques opens a huge amount of possibilities. And this is a workflow that I think should be deeply investigated by architectural engineering firms. And we have done a few projects following this. Basically, using Grasshopper, we can think that Grasshopper works, since Grasshopper is a kind of scripting language at the end, we can think that Grasshopper generates intermediate jobs. So we can think that it collects jobs coming from a first team, for example, and the data flow can be Rhino, Excel, again, another Rhino file from different people. Grasshopper connects this information and generates a new file. And again, this new file is again connected to other inputs from finite element analysis, CFD analysis. And so this workflow at the end can go into a final BIM server where you generate your model. The nice thing about this this workflow that we can split a very complex process into small processes and different people working at the same time on the same job. And it's really interesting implementing this. I have done it. We have done it in the office in a few times, but clearly the potential comes out when you have a very large staff and you can organize all these workflows into this workflow. Under Grasshopper, we have different tools available, and these are just a few that I know. BATS from Brazil, Rhino Membrane, IXCube, Kangaroo, Cable, Force Density, Kiwi from Professor Bletzinger. So basically, you can, as an architect, you can use a lot of different tools for doing your design. But design, remember, is only the first step. I want to underline this important thing when it comes to design tensile structures. Clearly, we go into the form finding step. After the form finding step, the engineer comes in and starts running an analysis. After the analysis, he checks that if everything is working. If it's validated, yes, we can go to the production stage. If not, we have to turn back. We have to review something on the project, and we go back to the form finding, and this loop will go on over and over until we get a viable solution. So this is what we do in a normal workflow. Using Grasshopper and generative design, we can change this workflow. You can see we start doing the design, and now we generate a Grasshopper script for the form finding. Then we do a check if the model is working after the analysis, and then we make a revision. If it doesn't work, we have to turn back and we go back to the form find. But since we have generated a parametric model, you see here that all the time that was spent generating different files in the previous workflow now is basically parametric. So we can, in a very fast way, we can loop over these iterations, changing the form finding, running the structural analysis, checking if it's feasible, and checking with the client. And so all the time spent making different models and checking them becomes very fast using this kind of technology. But you see that we have a clock on this. Generating a Grasshopper parametric model is something that takes generally a lot of time. So you have to take care that the time spent generating the model is most of the time, compared to the previous workflow. When we start generating the model, we draw a model, we check if it works. If it doesn't work, we turn back, we draw a different model, and we go on like that. So this was This is a short video that I have done a few years ago, but I think now this was in the beginning of Grasshopper. I think everybody now knows what Grasshopper is, and this is Rhino membrane running inside the Grasshopper environment. But basically, you see that you define your boundary parametrics, and the software will find out the surface, in this case, the pre-tested surface. And through your parameters, you can change your parameters to change basically the geometry. Well, clearly this video is quite old. It was the beginning. Now everybody knows this stuff. So I will skip it and go to the next step. Even this one is on Grasshopper, so I don't think you need it. To finish up, I just want to show you this as an example. We did a few years ago. They asked us to design, to renew this stage in Argentina. And basically, the architect sent us this initial concept. Now, the problem is with this concept from the architect, it clearly, the area here in the middle is it's not a tensile structure. You can see it's a convex shape, so it's more a shell structure. So basically, we needed to redesign this. We made a few concepts. At the end, the client said, "Okay, this was the concept that they wanted to use," and so we followed the process of generating files, generating Grasshopper scripts, and using Elefront, we were able to bake intermediate data into Elefront. So what we did a parametric model, and then baking different steps using Elefront. Elefront, the nice thing is that you can bake objects with properties. So then we can get back this database of objects, bake it in Rhino with Elefront data, and go to a next step. So for example, here we have file A and the process, and we generate file B. And this is the example. I will go fast on this video, but this is the example where we have generated the initial parametric model, because clearly when it comes to design, you have to make a design, then discuss with the client this design, and maybe make changes. So if you have generated the parametric model, it's easy to change the parameters and have different solutions to show at the client. I will skip over and go very fast over this. We will see this in here. We have designed the steel frame. I'll go over. Okay, so we will see this in using real examples. Now we are generating the second step, that was the membrane. And then clearly out of the initial model, we need to run an analysis to see if it's feasible. I will skip. I will go a little bit fast over these because they're quite. It's even in Italian here. But basically, generating the parametric model for the steel, for the membrane, running the first form finding. Clearly, then we want to run a structural analysis over these. So we can assign properties, the properties for the steel, the profiles, the quality for the membrane. And then out of the Grasshopper script, I'll go over a little bit. Yeah, we are inside Xcube, and we have generated the finite element model inside Xcube. I will skip over. This is the final model, and here we have, yeah, stresses, initial stresses, and stresses after structural analysis, and so on. So basically, it's clear that for you, that you're young guys, this seems quite common. But for, I mean, general workflows are quite different than these, because there are different people working on the project, and some of them are doing design, others are doing the structural analysis. At the end, someone is already doing the detailing and so on. So using techniques like parametric design inside Grasshopper, and being able to generate a lot of solutions and check them if they're available or not in a very fast way, makes a huge difference today. And this is the final, some slides of the final stresses. Clearly, we have run fluid flow analysis to check the wind flow over these. And even in this case, we can generate the wind analysis inside Grasshopper and generate the pressures on the surface to then to run structural analysis. Okay, I don't want to keep you so much on this. This is the process. We will see this. We will see this in using the software directory. Okay. So I will open my Rhino here. And then I have also my OpenXCube. The first thing that I want to show you is a few things about the software. The software is very large, has a huge amount of features, and clearly you will get lost if you don't know where and how to put your hands on it. Luckily, it's very similar to, if you know Rhino, it's very similar to Rhino. The right mouse click, you can rotate the window. Shift right mouse click, you can drag, and with the wheel you can zoom in and out. So this seems to be quite simple. If I start a new job, a new file, the software, these are templates, and the software is asking me what kind of template you want to use. The first density method, using meters and kilonewton, the natural first density method, the update reference strategy, on the same using inches and kip if you're coming from England. Clearly, we can change these. All the parameters can be changed later, but it's important that you start using common properties for the units, the length units, and the force units. We can change these going into options, preferences, units. We can change the units to whatever you want here, and the first units to whatever you want. For the form finder, we can also change the form finder from first density method, update reference. You don't have update reference strategy plugin, but to natural first density method. And then we'll see how to run also a nonlinear direct stiffness method. I want to start, another important thing, when we go in Rhino, start a new job in Rhino, clearly we want to set up, I will show you two methods because I see that the software is not, today, it's not fully compatible with Rhino 7. So if you have Rhino 7 and you're not going to use Grasshopper, then you have to save a file. In this case, I will show you how to import Rhino files, because generally what I do and what we do, I just Control C and Control V, and I paste data into the software. Okay, but this doesn't work if you're using Rhino 7. It will work in the next release. So if you're using Rhino 7, you have the file save as. You save as a Rhino 6 or a Rhino 5, sorry, a Rhino 5 model, and then we import the model inside XCube. We'll show an example in a few minutes. So the first thing, start a new job, you choose the method you want to use, and we are ready. Let's start making two examples, one using the force density method and one using the natural force density method. The basic difference between these two techniques, well, we have seen the math behind them, but basically the mathematical model that we see inside X-Cube will be different. Let's start making one. And again, I will start in Rhino. Generally, you start from Rhino because it's easier. I can also draw inside X-Cube, but clearly it's faster here. I just want to generate a very simple rectangular base, a very simple conical shape. So I just input here. I have made a square 10 meters by 10 meters. And then I just make a vertical line of 4 meters. And that's it. Select everything, explode this. And one thing that you must take care of when you're doing your initial design, always make layers and give a name to the layers. So boundary, the time you use to organize your structure in a correct and nice way will save you later a huge amount of time. So this is my boundary. Mast. I am telling you this because I see so many young people that they start and they call these layers 1, 2, 3, 4, 5, 6. Never, never. Maybe if you really don't know, this is construction. So always give a good name to the layers. Now I will save this file for people that are using Rhino 7. So save as. And I will call it Alto Con Test. So we go back to Xcube, file import. I search my file. And you see, I didn't save file.
You didn't save in Rhino 5. You saved in Rhino 6.
Oh yeah, saves. Thank you. You see, I have not used it to do this. That's why. Rhino 5. I have not used it to save files. Okay. Fine. You see, once we recall the import file, this is the same if you don't have Rhino and you're using AutoCAD or you have written a DXF or DWG file, you see exactly the same dialog box with the layers on the left. Now, each layer can be converted to one of these groups. What are these groups? Well, the tensor groups, I think it's quite simple. We model all the membranes are modeled inside tensor groups. Fem2D is a special group where we insert cables, beams, trusses, and linear elements that are connected to two nodes. That's why it's called Fem2D. We can convert surfaces, for example, to plates. Plates or stiff plates, plates like concrete plates or steel plates that have a thickness. Cushions are for ATFE cushions. We'll see this later. Boundary, it's an old feature we don't use anymore. And CAD layer is just CAD information. In this moment, I just select everything. I just convert it to CAD layer. Once we close, we'll find out that we have exactly the same information inside Xcube. Okay. If I start new again, and I go back to Rhino and I do Control C, Control V, clearly I get the same elements and I do exactly the same. So if you're using Rhino 6, this is a faster feature. If you're using Rhino 7, then you have to go through the file. Since I am lazy, I will go through copy, Control C, Control V when I show you these things. But remember that you cannot do it. You have to save a file. Okay. We have here just this boundary. Remember that we are using meters and kilonewton. I want to generate a simple conical shape using the force density method. The method that we are using is written here on the left of the window. So we are using in this moment the force density method. Generating the membrane, we can use one of these tools on the top left, and we have a tool called conical surface. So I will click on conical surface. And in this dialog box, it's asking me the number of points I want for each side. But we can also input. I want to input the mesh size. And so I want to input 0.5 by 0.5, and I click on mesh size. The software is waiting for my input. I just want to draw the edges, the 4 edges of this conical shape. C, I click it on the C to close. And now it's asking me where to place the top of the ring. We go onto the on the conical tip, put the size of the ring 0.25, and you choose if you want a beam element or not. I want to place a beam element, and then we just place it over the top. That's it. We have made the first mesh. So what we have seen is how to generate a mesh inside Xcube. In the next lessons, we will see how to do this all in Grasshopper. But now what I want to tell you, I want to let you see how the software manages tensor structures.
Jerry?
Yes?
Sorry for a short interruption. There is several questions in the chat saying iXcube asked for a license.
Oh yeah, for the license you have to send. There was one that was collecting licenses. Who was the name? You can send me an email. Wait. Oh, I can go into the chat. Let me find the chat. Oh, where is the chat window?
Maybe you can see it now.
You see, I'm writing on the screen.
Okay.
You can send an email to info@forten32.com. Write down your name, but if maybe it's better if you collect these license files. You have to go here, sorry, to get a license. Help license key. Copy paste this system ID into an email, and you send me an email. Or maybe you can send them to Gunther, and you collect an Excel file with all these system IDs with the name, and
yes.
then I will reply with your license codes. I will send you a license code that you put into this box here. Okay.
Yeah. Everybody who needs that, please send me an email.
So you just have to get this system ID with your name. You send an email, and you'll get back a license code to pass into this box. How do I clear this text? Ah, nice. Nice. I never used Zoom to do this, so it's the first. We have generated a conical mesh. Okay. First of all, let's see what has been generated. The first we have here on the left side, the tree browser. This is the model browser. The model browser is a collection of layers You can make a new layer here and call it steel, whatever it is. So we have a collection of layers, and inside the layers, we have, like any other CAD software, we have data. In Xcube, we have two different kinds of data. We have CAD data and FEM data, because the software is a FEM tool and a CAD tool. FEM data is collected into groups. So we see here that we have a group called C1, and under the group, we have a mesh. This is the mesh of the group. If we hide the mesh, we see these lines here. These lines are the so-called springs. You remember that when we are talking about the first density method, we said that the first density method uses springs and nodes connected to the springs. If we unhide the nodes, we see here that we have these nodes here, and here we have the springs that connect to these nodes. So we're using the first density method, so we have this grid of springs and nodes. Then we have a mesh. This is a mesh made out of triangles, and this mesh is used when we are using the first density method. We use the mesh for applying loads, wind loads, pressure loads, snow loads. And then we use it for making patterning. Clearly, we cut the mesh, making out patterns. But the mesh is not a structural element. The structural part is these links of membrane. These are links of membrane. So you see we have a group. This group is a tensor group. Then we have another group, a FEM2D group. You remember that we have seen when we have imported the file, you can generate a FEM2D group. A FEM2D group is a group made of simple elements that connect to nodes. In this case, the software has generated chains. What is a chain? A chain is a number of elements that he connects all together in a single finite element. So it's easy to change the properties. For example, I want this element to be a cable, or I want it to be a beam. I can just select beam, linear, and choose the cross section. So we can change in one shot the properties for all the elements. Before going on, let's give a look at these properties. I've opened it here, the Seed browser. You'll find this in Tables, Database Explorer. What do we have in the Database Explorer? Well, we have a list of materials. You can see we have steel materials, concrete materials, membrane, wood, and aluminum materials. And then we have a list of profiles, different kind of profiles. You can make your own profile if you want. For example, I can clone one of these, change the name of the profile. I want it 500 by 500 by 10 millimeters thickness. This is just the name of the profile. And so in the base, we can open it here. So let me open the window. The properties, I want it to be 500 millimeters. Remember that we are using meters as the unit. So you see here, he's printing meters. But you can write 500 mm, and he will convert it to meters. And then the thickness is 10 mm. Once we have changed the geometrical properties, we need to click on this, compute the properties of this cross section, and the software will get out with the area, the inertia.
Hi, pardon me, please.
Tell me.
I cannot see your IceCube window because I am only watching the screen from Rhino source from 10 to 15 minutes ago.
Really?
Yes.
Everybody, nobody sees my screen?
I can see.
Yes,
I can see.
I can see it too.
But I think there is problem in my Zoom, I think. What I should do?
You can restart your thing.
Okay, sir. I'll join you in a second.
So you see Rhino. So you have a time machine. You're saying something that's half an hour faster. It seems to be blocked. Maybe you should restart Zoom.
But what I see is quite normal. It's just smooth.
Does everybody see the profile in this moment?
Yeah.
Yes.
I can see.
Yes.
A square orange profile.
Yes.
Yes, we can see.
Yeah.
So restart the Zoom and go on. So basically what we have done, we have created a new steel profile, okay? And you have different profiles here. Generally, we use the circular profiles for tensile structures. And there is a reason why we use these profiles. Maybe we will see it later in the analysis, but when we run structural analysis on a tensile structure, generally what happens, the shape goes under large displacements. And when it goes under large displacements, it means that the forces, the direction of the connection forces is changing quite a lot. And this means that if, for example, if we use as a boundary beam a rectangular profile or an E profile, it's impossible to catch the strength, the inertia in the direction that we want. I will show you better this one. Clearly, it's easier to use a circular profile if the force acting on this one changes direction. The stiffness of the profile is equal in all directions. The reason why you see you mainly see circular profiles in tensors. Anyway, you can make your profile here. Then we go into the material database. Under the membrane material, you'll find out a number of pre-made materials. And looking at the membrane properties, if we look at the conventional steel, you'll find out the properties that you see in any finite element program. It wants the E modulus, the Poisson value, the density, and the thermal expansion value. Then we find under the extended data, extended properties that are used to design the steel, to check the steel for Eurocodes or American standards and so on. This is almost the same for all materials, but when we go into a membrane material, these values change a little bit. First of all, we find that we have two different E modulus, one for warp and one for... You don't see very well my text because I have a large fonts on this monitor. But
We can see very well.
You see them?
Yeah, I can see them.
So basically we have two E modulus, one for warp and one for weft. Because remember, the membrane is a woven material. We have a warp fiber and a weft fiber, and the behavior generally is nonlinear. We never model nonlinear behavior, even if you want. We have a feature here for modeling nonlinear materials. I have an example here, Ferri nonlinear material, where we can make a nonlinear material. But in this case, we have to make a script where we define the behavior of the material. This is a complex topic. Let's turn back to a normal one. Turn back to a normal Ferrari pre-constraint. So we have the E modulus in warp and in weft, the density of the membrane, the weight of the membrane, the thermal expansion value. And then we have again the Poisson of the membrane, the shear value, and the thickness of the membrane. Now, one thing that you must give a look at, the membrane properties are all defined in kilonewton per meter. If you're an engineer, generally properties, E modulus is a force over a squared area, kilonewtons per square meter or kilograms per centimeter squared centimeter. When we use membranes, we never take in account the thickness of the membrane. So any paper that you see out there where membranes are involved, in 90% of the cases, you'll read the stresses of the membrane as kilonewtons per meter or kilograms per centimeter, whatever you want, but never megapascal. Because the thickness of the membrane, we cannot change it. It's something related to the type of the membrane. So we just throw away the thickness and we think in terms of a force over a length. Okay, is that clear? It has to be clear because it's very important. Again, in the extended data, we find out the braking load for the warp direction and for the weft direction. This braking load will be used when we check the membrane to see if it's feasible under the load scenarios that we have done. In any case, from a material and from a profile, so joining a profile and the material, we generate a seed. You see here on the right side, we have a database of seed elements, and these are just a profile and a material. So clearly you can make a profile, a wood profile, a steel profile, an aluminum profile, and whatsoever. The only difference is for the membranes. The membranes do not need a profile clearly. The membrane needs only the material. If you want to generate one of these seeds, it's very simple. You choose the profile. Let's make a new cable, 18 millimeter. You right click on the cable, create a new seed from this profile. And you'll see here that this one comes out here. We have generated a seed with the cable 18 millimeter, but we have no material assigned. So we go into the material database. We go into the steel. We have a special steel called steel cables. Right click, apply this material to the selected seed. And now you see that the cable 18 millimeter now has steel cables as the material and cable 18 as the profile. You can change the name, right click, rename as profile, rename as material, or rename to both. Rename to both, now it's called cable 18 steel cables. A double click will move it into the model database. So this one up here is a fixed database. The bottom pane is your model database, the properties that you want to use into your model. So we have just moved the cable 18 millimeter cable into the model database. You close with OK, and if I click on one of these elements in the properties, I will find out now that I have the cable 18 millimeter steel cables. Okay, that was easy. Yeah, it's easy. You're smart young people out there. Okay, we still have this mesh here. Remember that you can create any layer that you want. For example, if I make my membrane layer, I call it membrane, and you can drag a group from one layer to another. The reason for this is always the same. We want a nice organization of our job. Think that if you have 100 groups in different membrane groups, steel groups, cable groups, and so on, for the purpose of a nice work organization, I want to split these in different layers and organize in different groups so it's easier to check them and to hide and unhide and so on. So basically, we model membranes and tensor groups. I want to make a new layer, and I call it my edges. And I drop my edges onto this new group here. So my edges are in this group, and my membrane is in this other group. These are just my graphical groups that we have imported from Rhino. Okay, let's go on. What we're using for running the form finder is, sorry, let me tell you, one special group is the FEM nodes. The FEM nodes are these dots here. So you can unhide the nodes from this layer here, or from this tool, it's easier here. the nodes are FEM nodes. Now, for engineers out there, I don't need to say anything about what a FEM node is. For the architects that do not know what really a FEM node is, when we are running a finite element analysis over these. It's not really a CAD software. We run analysis. When you want to run analysis, the model that we generate has to be correct from a finite element point of view. And that means it has to be a topology of elements. Let me draw here. Draw. If I want to draw, I will draw over my window. If I want to draw a mast, no, what's this? Draw. Okay. Yeah. Let's say that I want to draw. Well, 1 second. I am learning how to do this. Okay. I want to draw a mast. And this mast is connected. I have another steel element like this. Okay. If you draw this mast in AutoCAD or in Rhino, you cannot draw one line from here to here and another line from here to here. They will not be connected. The finite element program will make one steel element that goes from this point to this point, from this point to this point, and another steel element that goes from this point to this point. So when you run analysis, you'll see that these two elements will not be connected. To be connected, they always have to be connected on the node. And this means that we have to basically draw in the CAD program one line like this, another line like this, and another line like this. When you do this, the software will make a node here, and all the elements are connected at this point. This is very simple, but people, many times I see quite often that people don't do it, and they send me files that all the steel is collapsing. So your steel frame has to be, from a finite element point of view, a correct topology. Clear, clear. Where is clear? There's no clear. Okay. So let's turn back to the model. Now, this is our first density net. You see that when I click on one of these elements, the element is selected. When you select an element, let me talk two words about selection. You will make some exercises. If you want to select an element, you can just go and click on it. You can open a window and he will select all the elements inside the window. You can open a window. If you open it from left to right, the software will select all the elements that are inside and have been cut by the window. If you open a window from from left to right, sorry. In this case, from left to right, he will select the elements that are inside the window. So from left to right, inside the window, from right to left, inside and cutting the window. If you use the Control key, if you keep the Control key down, you will deselect selected elements. Okay. Then we have selection tools here. You can select, for example, by circle. You can select by polyline. Okay. And once you have a selection, if you write a name here, S1, you can save your selection. So basically, if I want to recall my selection, I just recall S1 and I have my selection here. This because generally the workflow is very simple. we select entities, we select objects, and we change properties to these objects. Okay, so this is 90% of your work is selecting and changing properties. Now let's give a look. When we select entities, we see the properties of the entities in this window here. This is the property browser. In the property browser, we see that some lines are white and some lines are green. What does this mean? It's very easy. When you see a green, we have a multi-selection. We have selected many entities. And you see that if I collapse these, we have selected nodes and elements. When you make a multi-selection, the green lines means, look, you have selected many elements and the properties of these elements are different. They don't share the same property. In this case, you see a green line. If you see a white line, it means that all the elements have the same property. Okay. So, for example, if I go into the nodes, all these nodes have been selected. The Z is 0. Clearly, when you see a green line, you're not looking at the properties of the elements. You're looking at the property of the first element of the list. It's clear, no? If I change this one to 0.5, you see that all the nodes have changed their position to 0.5. Okay. Let me undo. Oh, I cannot undo that. Sorry. Made a mistake. Anyway, let me do it again. It becomes an exercise. I have done the undo, but the undo just deleted my group. It was the last command that I am using. Okay. I have generated again my two groups. So basically, we have learned it. Select objects and change properties for the selected objects. Okay. Another thing to understand, what I am trying to do is to start giving you information that you don't get crazy later. It can happen that you have CAD tools. You have CAD entities. For example, if I enter the CAD entities and I draw a box, okay, this object here is a CAD entity and it belongs to the layer 0 because 0 was active. This green dot that we see near the layer is the active layer, like any other CAD software. So if I want to change this layer and I want to put it on default, I can go here and they say this one is on default layer. Okay. So you can hide your CAD layers by just closing the default layer. And there's a fast tool here. In the FEM tools, there is a fast hide. Hide all the FEM entities, or unhide all, the CAD entities. Hide all the FEM entities, unhide all the FEM entities. Okay. So if your model starts getting quite complex, it can happen that you don't understand what is FEM and what is CAD. Okay. If this happens, you just go here, you hide all the CAD entities, and what you see are FEM entities, or vice versa. Okay. Now, let's turn back to the main problem of running the Form Finder. Remember, we are using the first density method. And we want to assign properties to the membrane and to the edges of the membrane. First thing that way, I want the edges to be fully fixed. So I click on the edges. You see, these are my 4 boundary edges. And I'm not really interested in the structural behavior of these edges in this moment. I don't want to run a structural analysis keeping in mind of these steel elements. So these edges, I want them to be beam elements. I want them to be linear. You always flag beam elements to be linear. Okay. I want them to be fixed. And then we can assign a profile. So basically, we have fixed the membrane on these beam elements. Now, I'm hiding the mesh. I'm hiding also the nodes. We want to assign properties to the mesh. Remember, we're using the force density method, so these are my springs. You can just double click. One important thing to understand, sorry. You see under the at the bottom of the window here, there are a number of buttons that you can say uncheck and check. These buttons are selection filters. So if I click on known, I have deselected all the filters. If I try to select something, I'm not able to select anything, for the simple reason that all the filters are checked off. If I want to select, if I want to be sure to be able to select, you can click here on the all, so all the filters are active, so I am able to select the entities. Later we will see how to use these in an easier way, but keep in mind that if you're going crazy and you're not able to select, just click on the filter all and start selecting. To select all the entities in a group, you just double click on the group. You see, he has selected all the elements of the group. Now, these are the membrane elements. The type has to be this special membrane. Do not choose the type. Do not change the type of the element if you're using the force density method. This has to be membrane. The behavior is nonlinear, and the deformability is form-fine deformable. Later, I will explain you the difference between form-fine deformable, stiff deformable, and fixed. We will learn how to use these because if we want to merge a membrane with the steel, we have to define which part is deformable by the form finder and which part is not deformable or stiff deformable. It means that yes, it deforms, but it deforms under loads and not because we want to find the shape. So this is form-fine deformable. It means, look, I want to find the shape of this net. So I put it into the form-fine deformable. I put it as a form-fine deformable type. Then we choose a material. In this case, I would just choose a pre-constrained 702 fairly. And then we have the C value. The C, if you remember my initial discussion about the force density method, the C value is the force density. It's the ratio between the force in the element and the length of the element. But this in the final geometry. We will leave it to 1. Okay, let me save this. Oh, this is okay. And now we can run the form finder. We have here 2 form finders, a form find stiff and a form finder. You can use the form find stiff when you do not want to take care of the steel. So you just run the form find stiff and you see that the software has relaxed the shape into a conical shape, quite ugly conical shape. Before going to change the shape, let's give a look at the stresses in the shape. We go into the response here. We choose response after the form finding step. And since we're using the force density method, I want to give a look at the principal stresses in the membrane. So these are the stresses in the membrane. And you see that we have a blue all the blue area is 0.9, 1.9. So the range goes from 0.9 to 1.9, but what? Kilonewtons per meter. So the stress, this is the sigma 1. It's the principal stress. You know, in a membrane, maybe somebody doesn't know. Let me draw. Let me draw for the non-engineers. If this is a membrane, we have in a membrane these stresses okay, oh, ugly arrow, and we have also these stresses. This stress here is sigma xx. Do you see it? Do you see it?
Yes.
Yes.
Because it's blue, I don't see it. So anyway, this vector, this stress here is sigma xx. This stress here is sigma yy. And then we have this one is sigma yx. It's called the shear. And this one is the other shear. And generally, the shear stresses are the same. Okay. So these are called the local stresses. We will see these local stresses when we talk about the natural force density method. These are the stresses in, remember that we have defined for the membrane element, we have defined the axis of the element. So if these are the local axes of the element, this is X and this is Y, and then we have a sigma XX stress and a sigma Y stress and two shear stresses. These are the stresses in the local axis. These stresses we can find if we rotate the axis. If we want to find the stresses, for example, in this plane, normal to this axis, in this plane we have also a stress that we call Sn. This is the stress with this normal direction. Now what happens? There are two orthogonal directions where we have the principal stresses. These are the maximum and the minimum stresses. Okay. So if we rotate the axis, this is a membrane element. If we rotate this vector normal here, 360 degrees, for each normal plane, we find the stress value. There are two orthogonal values where we find the maximum stress and the minimum stress. And these are called the principal sigma 1 and the principal sigma 2. Okay. Is there erase everything here? No. Oh, clear. All drawings, I found it. So basically, what we are looking at in this moment is the sigma 1 stress. This is the maximum stress in the membrane. Clear? We can plot the sigma 2 stress. This is the minimum stress. We see that the minimum stress is again positive. We have 0.5 is the minimum value, 0.05 here is the minimal value, and 0.9 is the maximum value, but they're still positive. The reason they're positive is because we are doing a form finding. This was the aim of the form finding. Find a shape where we have a positive stress in any point. One thing that you can ask is, okay, but which is the y and which is the wave direction? And here we have an option, sigma 1, sigma 2 direction, And we see these two arrows here, the red one and the blue. The red is the sigma 1 stress and the blue is the sigma 2 stress. It's nice to see on the top point, look how high the stresses are. If we go back to the sigma 1, we see that the stresses are very high on this conical shape, and the stress direction goes, this is the direction. The sigma 2 stresses are very low. You see that they are going to 0 here. Around the conical shape, the stresses are going to 0. If we look at the stress direction, we see that the blue is very small here. What does this mean? The software is giving us a very important information. It's telling us, be careful that when you go and you build this tensile structure, it's likely that you get wrinkles in this red direction. Because if we get a membrane and we pull it with a very high stress in one direction, in the opposite direction, the stress is very low. You'll see wrinkles in the direction of the high stresses. No? Is that clear? Try to get a tissue and give a high tension in one direction, and you'll see wrinkles in the direction of the high stresses. Again, if we look at this corner here, you see that in this corner, here we have a weft stress, or the sigma 2 stress is very small, but here it has disappeared. There's no stress at all. If we turn back and we look at the stresses, we see again that the stresses are very, very low here. Again, it means that if you build this membrane, it's likely that you get stresses in this direction. In this direction, sorry, white. In this direction, you can get wrinkles. Okay, so it's important to understand how to read this information. Okay. Now, let's turn back to the shape. We have run a form finding. As architects, clearly, we want to change the shape of the model. How do we change the shape of the model? When you're running a form finder, any kind of form finder, the basic way to change the shape is change the level of pre-stress. In this case, we want to change the pre-stress in the rings to have more curvature in this conical shape. So we go back. We have here a selection tool, call it weft curves. And you see, he selects all the ring elements. We go into the properties, and for the C value, remember the C value is the first density value. It's proportional to the stress in the membrane. We put a value of 3. We run the form finder again, and you see that we have found a new shape. If we go back and we plot for the form finding the stresses, you see, we see that the stresses have changed. 1.5, 0.15, but not so much. What has changed? These are the sigma 1 stresses. What has changed? Oh yeah, these are the sigma 2 stresses, sorry. The sigma 2 stresses have changed because we have increased the stress for these weft directions. Okay. One thing to say about the first density method, it's a bit complex in the beginning because the C value has nothing to do with engineering values. Now, it's not a pre-stress, it's not a force. It's a ratio between a force and a length. So how can I understand the value to input as the C value? Well, in the beginning, it seems a little bit difficult, but if you start joking with these, it's not really difficult. And I will explain why with a sketch. We have again a membrane. This is the first density membrane. So these are links. Okay. And these are my nodes. Okay. So this element is a spring element. And we have a force here. Okay. And then we have the length. Okay. The C value is the force over the length. So this force over this length. This is the force in this element. But if we think that this is not made of links, but it's a membrane, let's give a look at this membrane here. This membrane that's on top of the middle point. The stress of this membrane is the force over the width. Okay. What is the width? The width is this side here. From here to here, this is V. Is this clear? The stress is a force over a length. The stress, the sigma x stress in this on this side is this force here over V, W. Okay. Now we have found that the C value is the force over the length. This is the force and this is the length. I see you scared. Don't be scared. Now let's think that the grid, to make things simple, let's think that the grid is a square grid. So if the grid is a square grid, this length here is equal to W. If we have a square grid, the length is equal to W. Okay. So the stress becomes, let me write here. SX becomes the force over L. So basically, the C value is proportional to the stress if we have a square grid. Is that clear? No, it's not clear. Anyway, it doesn't matter. When we input the C values, clearly the value of the C value will change if we have a grid that is not a square grid. But the reason why we have different C values for the y direction and for the west direction. But from a scale point of view, when we input a 1 for the C value, you can think as a 1 kilonewton per meter if you're using a kilonewton as forces and meters and length, and the grid is almost 1 meter. So at the end, it's very simple to input the C values. If you're not sure, it doesn't really matter. What you can do is you input your C values, you look at the final stresses, and if they do not agree with what you expect, we could change them quite easily. What does this mean? The first density method is a linear system. So, for example, I want to scale the C values without changing the shape. If I want to scale the C values, this means that I want to scale the level of priestess, but I don't want to change the shape. I like this shape. I want to keep the shape, but the priestess, I want to change the level of priestess. We can just select everything. We can go into edit, change behavior, and multiply the C values, for example, by 10. So we're scaling all the C values by a constant factor. If we do this, and we run the form finding again, you see that the shape has not changed. Scaling the C values does not change the shape. Scaling the C values has only scaled the priestesses. If we go and look at the priestesses again, we see now that the values have been scaled 10 times. What does this mean? It means that when we're using the first density method and we want to find a shape, what is important is not the overall value of the first density, but the relationship between the first densities, the ratio between the warp and the weft first densities. This ratio will give you the shape. The overall value will give you the stress. But we can find out, after finding a nice shape, we can scale the first densities that they are inside a range that fits our needs. Okay. So in the beginning, you can joke with any value, any C value. When it's time to run the analysis, I mean, when we have to go from the form finding step to the structural analysis step, then we have to check these stresses. And if they do not match the stresses that we require, we have to scale the C values. Okay.
Can I ask
Fine. So basically, this is the first density method. I will save this and start a new job using the natural first density method.
Maybe there was a question.
Oh, yeah. Let me see the
yeah,
chat.
Gary, can you hear me?
Yes, I hear you. Tell me.
Yeah, thank you. And I was trying to understand that the reason that why we scale the C value is that you mentioned it before, we like trying to avoiding the wing during the surface.
Sorry, can you repeat? Sorry.
I mean, the purpose that we trying to find the balance of the C value of the first density in the whole surface is like trying to avoiding the weight on the surface.
Yes. The C values govern the shape and the level of priestess in the membrane. Now, in the initial stage, we are searching for a shape. Okay.
Yeah.
How do we shape the membrane? We shape the membrane by changing the priestess of the membrane. Clearly, we have also the boundary edges. In this case, everything was fixed, but generally, we have also cable boundaries edges, so we can change the shape of the cable boundary. But in the beginning, we want to find a shape that fits our design. How do we do this? We do this by changing the level of pretension in the membrane.
Yeah.
But since the C values have no really connection with real physical numbers, in the beginning, it can be difficult to understand what C values I have to use. But the number is not really important in the form finding step. You can choose any number. What's important is the ratio between the numbers. The ratio between the first densities will give you the shape. This only for the initial design phase. Then what happens? Once I have a shape, we want to go to the next step. The next step is I want to start running a structural analysis. I want to apply the wind loads, the snow loads. I want to connect my membrane to the steel frame. So the initial precess has to be a feasible precess, a real world precess. So I have to look at the initial precess, and if the precess is too high or is too low, I have to scale it to be in the range of feasible precesses. Just to give you an idea, a feasible precess for a small or medium structure goes from 0.7 to 2 kilonewtons per meter. Okay. For the conical shape, it's a bit different. Let me reload the conical shape. The conical shapes have a problem on the tip point. Let me select everything again. I will scale back because I know for this conical shape, the values of 1 and 3, 1 for the warp and 3 for the weft, are almost correct values. But because I know that they are correct values, clearly you don't know that. I will scale them back. So I will edit, I will change behavior, and I will scale them 0.1 to let them turn back to the original one, to the original values. I will run the form finding and plot again the stresses in the membrane. You see, oh, this happens for the range. The blue range is almost 1.7, 2.5. Okay. Maybe I have to scale a little bit down, but on the tip point, we have a stress of 12 kilonewtons per meter. That's quite high for an initial precess. So clearly, I have to go a little bit down. Maybe we have to scale down these elements. I will select again all the membranes. I will choose edit, change behavior, and scale them again 0.6. I will run the form finder again. You see that when I run the form finder, the shape doesn't change anymore because I am scaling. We are multiplying all the first densities by a constant value. And this means that the ratio between the first densities is kept the same. And that means that the shape is not changing. We are just scaling the precess. And let's give a look again at the stresses. And you see now I have a 1 up to this blue. We have a precess of 1 up to 1.9 kilonewtons per meter for the warp direction. And then we have here on the tip point a 7 kilonewtons per meter. Now, I don't know, but if you look at many conical shapes, built conical shapes, you'll see that many of them here have a double or a triple layer of membrane. Because clearly what happens is that when we run analysis, the stresses, these stresses will go higher. And this is true for any conical shape. You just have to think that this is filled with water, like a tube with water coming in. The pressure of the water is very low on the boundary, but then this water, when it goes to the small hole, the pressure increases because the hole comes smaller. It's exactly the same. The equilibrium of these stresses over this large boundary edge has to be equilibrated by the stresses of the small ring. So clearly the stresses have to be quite higher. But for conical shapes, this is always like this. Okay. The reason why, when we're using the first density method, your first problem is finding a nice balance between the first densities to find the shape. And then we scale it down to, in this case, a good range. You see that everything is almost blue, 1.51 kilonewtons per meter, so it's okay. And clearly here, on the top part, we will need to reinforce this membrane with a double layer or maybe a triple layer. This depends now on the structural analysis. Okay. Let's give a look. We have 10 minutes left.
Maybe, Jerry,
yeah,
maybe we can add one more aspect to that, which is related to this question. you predefined the square boundary and you predefined the central ring.
Yes. Yeah.
And then you generated the mesh in between, and then you kind of pretensioned the whole thing.
Yes.
If you would do that, as you explained earlier with the soap film, the soap film would not work here because the ring in the center is too small.
Exactly. Yeah,
So
exactly.
the soap film would just pop off. So
exactly.
because the soap film would try to equalize or to find an equilibrium in the forces in all directions to be the same. So this geometry of the boundaries of the ring and the square does not provide a chance, geometrically, a chance to have similar or equal circles of curvature.
Yes.
And that's why it's not a minimal surface, and that's why the forces have to be different. If you force it to be like this, you could change it in terms of changing the radius of the ring.
Exactly.
If you provide more length, you could change like the diameter of the ring, and then you could see how the forces would go down on the peak.
Exactly.
Or another option would be to go lower with this tipping point, and then again the forces would go lower because the radius changes.
Exactly.
Maybe this helps you also for your question.
Let's demonstrate what you're saying, because it's interesting as a topic. This is something nice. First of all, this is something nice when you need to find a shape that is not a minimal surface or a constant stress surface. The first density method is very powerful because it forgives, it's able to do a lot of things. But let's try to do a minimal surface now. So I will save this, save as.
Hi, I cannot hear you anymore.
You hear me now? You hear me? Everybody hears me?
We can hear.
Say hello.
Yes, we can hear you.
NFDM. I will save as NFDM. Okay. I will go into options, preferences, form finder, and switch to natural first density method. Now we are using the natural first density method. The natural first density method means that these triangular elements are the finite elements now. Okay. I don't need the grid anymore. So I will select all. I will take off mesh. I'm going to select my grid elements, and I'm going to delete them. Okay. We are not using the first density method. We are using the natural first density method. I unhide my mesh. Now my mesh, this mesh here, is the soap film. If I double click on the mesh, oh, I have to activate my filter. If I double click on the mesh now, you see that now we see properties on the mesh. If you try to do this using the first density method, you don't see any property on the mesh because they are not finite elements. Now we have switched the method, we have deleted the links, and we have moved it to the natural first density method. And now the mesh are finite elements. We are going to do the form finding over using these as the finite elements. And we want to have, I will put the material, a stress 1 by 1 stress means a minimal surface. When you choose for a surface, for a membrane, a constant stress, in this case you see 1, 1, means that I want to find a minimal surface over this membrane. If I run the form finder, you see that the software is asking me how many loops you want to choose. Clearly, it's a nonlinear problem, so we have to use more than one step. 5 steps. You say, okay. That's it. This is the minimal surface he has found. So you see, the minimal surface is a flat area, this thin line in the middle, and that's it. So clearly you understand that there is no minimal surface that satisfies this condition. You cannot design this conical shape using a minimal surface. You say, okay, but how do I, if I want to use the, I will roll back. If I want to use the natural force density method, I want to find this shape. Well, if you want to find this shape, I will run again. We have to put inside this membrane, we have to put some cables or some links that avoid the problem, that fix the problem that this membrane tends to collapse in the middle line. Okay. If I run another, I will run another version of the program. I am opening another I will get back my my previous file. My previous file is yeah, and it was cone. Okay. What I want to do is I want to get some of these links. I want them to be cables. So I will use this tool here. I will do it very fast. I will select some of these. I will do it like this, very, very fast. I don't want this. I don't want this. Okay, I'll just use these. I will do Control C. Go back to this one here, Control V. And those elements are, I don't know what they are, maybe this one. I will put all of them into boundary mask. I don't know which layer. Then still membrane. And membrane, I will put them in FEM2D. No, it was not membrane. Okay. So I just made a copy paste of those lines into the model. These elements, so I have generated these FEM elements. I will put them as cable elements, non-linear, form-find deformable, and cable 16. And clearly, I will put a very low priestess of these, 0.1 pretension. And now we run the form finding again. Oh, I have to give a little bit more pretension. Let's put it to 5, 10 maybe. So they need pretension to keep the membrane not collapsing in the middle. Now, it's a bit too much now. So here you start understanding how the other technique works. Let's put it to 4, 3. I don't do this quite often. Anyway, you understand that to do a conical shape using the natural force density method, if we do not put these edge cables, you're not able to do this kind of form finding. And here, for example, is the big difference between force density method and the other techniques. The problem is not the technique. The problem is that when we assign when I click on the mesh, you see that we have the option to give a stress for the wipe direction, a constant value, and a constant value for the weft direction. In the reality, this membrane needs a linear stress. We should say, look, that here the stress is 6, 5, 4, 3, 2, 1. So we should be able to give a linear stress field, but that becomes difficult from a practical point of view. Okay. Anyway, we are nearly at the end. So maybe just time to show how the force density works. The natural force density works for an IPAR method. Let me go back to Rhino. Let's make an IPAR. I will just move this and then copy here. And then I will draw the boundary of an IPAR. Explode it. Now I copy this boundary and I paste it and as a CAD layer. So I want to make an IPAR out of this boundary. And now we are using the natural force density method. That is very much more simpler when it comes to make these kind of shapes. I just select my edges, and now we go into the FEM tools, and we have a tool called Sew and Merge. Sew and Merge is asking me the size of the mesh. This is 10 meters, so I'll put 0.3 by 0.25 by 25, 0.25 by 0.25. You say OK. And he has generated this mesh over that boundary. We have a mesh. What we need is the boundary edges of this mesh. And we have another tool here, boundary, all mesh boundary. You click on all mesh boundary, and you see he shows this dot here. This dot means, look, I am going to create a boundary that starts at this point, starts in this point, goes all over the edge, and closes again in this point. We don't want that. I want 4 edges. Here in the options, we have a value named angle deviation. You click on this value and you input an angle, a small angle like 60 degrees. You see now that changing the angle, he has found the 4 corner points. So he will generate one edge here, one edge there, and so on. So you just click on apply. Now we have the edges. These are the edges. The software generated a group called mesh edges and 4 chains. These are the 4 edges. So we want that these edges to be cable elements. They have non-linear behavior. Form find deformable, yes, I want them to be part of the membrane. We choose a cable, 16mm diameter cable. And now the huge difference between the natural force density method and the force density method is that now we have to input the pretension of the cable. In this case, I would put a 10 kilonewton pretension. If this was a force density, instead of the natural force density, I was going to read here, input the C value of this edge, the force density value. In this case, it's asking me the pretension in force units. Okay. Now we go, you see that if I hide the mesh, if we hide the mesh, we have no springs inside here. We are using the mesh as the final element double click on the mesh, and we see the properties of this mesh. Again, we want the warp and the weft pre-stress to be 1 kilonewton per meter, and again we choose the material. Let's hide the nodes. Clearly, these nodes are all, by default, the nodes are free. What does free mean? Free means that the node is not constrained. Clearly, we need to fix at least a few nodes, in this case 4 nodes, if the node is not fixed, it will move around and all this model will collapse in a single point. So we need to select the 4 corner points and fix them to avoid that they move. So we select them. You see that we have here the stiff resting. You can just click here, fix it, and these points become red. That means that they are fully fixed. We are almost done. There's one thing that is missing, and this is iPilot. One thing is missing, and one thing that I didn't even tell you in the first density method. What is warp and what is weft? In the first density method, we have a net where the direction of the fibers tells the software what is the warp direction and what is the weft direction. Now we have a finite element triangle mesh. And so how can we tell the software what is warp and what is weft? Well, basically we do this by setting this property here. We have a tool under the mesh, warp weft mapping, set warp weft orientation. If you remember the initial speech, I was telling you that for an iPilot, the main stress direction goes from high point to high point, low point to low point. So we want that the warp is this direction here. This direction is the warp. And this direction here is the weft. If we don't do this, the software by default has set up that this is the warp and this is the weft. And that's not correct. So how do we do it? It's very easy. We go into the UCS here, UCS X-axis, and we just click on these 2 endpoints here. So you see we have rotated the main plane to be at 45 degrees. Now you right click on the mesh, warp weft mapping, set warp weft plane. The current UCS plane, the XZ plane, so the plane that is cutting the surface on this line, is the warp plane. And you just click on OK. So now we have set that this direction is the warp direction and this one is the weft. So we can save and we can run the form finder. You can just input one step. That's it. This is the iPilot. And if we look at the stresses, since now we are using the natural first density method, we can give a look at the sigma XX stresses. These are the warp stresses. And the sigma epsilon stresses. These are the weft stresses. One thing that we can see that we have the stresses that go from 2 down to 0.4. But we have made only one iteration. Clearly, more iterations we make and more the stresses, the stress field, will reach the value of 1. So let's recall the form finder. Let's input 5 steps and run it again. Okay. Now we can plot again the stresses. And you see now that the stresses go from 1.09 down to 0.94. So basically, it's almost a minimal surface. Okay. Sigma, these are the weft. You see red here. If I switch from warp to weft, you see how the red changes. These are sigma X6, sigma YY. And then if we look at the von Mises stresses, the von Mises stresses are a mixture between the sigma XX and the sigma YY. And you see basically that we have almost 1 here. Okay, so basically we have found a minimal surface. Are you happy?
Yes.
Be happy because we have finished. And for today, I think that's enough. No? Anybody questions? Nobody has questions. That's good.
So it was clear.
I hope so. Well, in the beginning, it's a bit difficult, but then as soon as you make a few models, everything will become quite clear. In any case, if you go on, everybody sees the chat, no?
Yeah.
If you go on www.vimeo.com and you search for AX Cube, you'll find a lot of video tutorials on how to use the software. So you can, again, on the website, in the Learning Center, there are a lot of video tutorials again that you can look at. So you'll find a huge amount of information on how to start. But basically, if you do after doing a few models, you'll find your way. Okay. Remember to send the licenses to Gunther for getting the key.
Yes, that's what I wanted to mention. I received already 5 or 6 emails. Most of you are missing, so please send me these codes from the machine code, this ID, to my email, and I will forward it to Jerry in one email. It would be good if you can do this today, so that you can use it during the week until our next meeting at Thursday again, same time.
There's one thing I want to say. Maybe if somebody is using not NVIDIA graphic cards, but ATI graphic cards, maybe if they don't have the latest OpenGL drivers, it can crash. You can face a crash when you show nodes here. If this happens, send me an email and I will tell you how to fix it.
Okay.
But it's for ATI graphic adapters.
Okay.
Okay.
Good. So thanks for today, Jerry. And for all the participants, please send me this email. Don't forget to do it today. And I will forward everything to Jerry and get back to you by email again, with the keys, so that you can use the software and that you can prepare things for next week, so that you're kind of like already can kind of redo what Jerry demonstrated.
Yeah, I suggest exactly. You just the conical shape and the iPad.
Yes, that's my suggestion. So you get into it and you can follow step by step. I try to provide also the recording, so you can kind of follow these steps and redo the thing for next week. Okay, if there are no further questions, I would like to thank you all for participating, and especially for Jerry for spending your time with us and showing us this introduction to your software.
It's been a pleasure. Okay.
Thank you very much.
Thanks a lot, and see you next week.
Bye.
See you.
Bye.